TKNS. We are doing the electro-hydraulic control system kit for MELAB 4733. I'm Kayla, and I did SolidWorks and hydraulic design. This is Emmett. He did sim hydraulics and fabrication, and remodeling on LabVIEW control and safety system design, as well as part acquisition, and David Richardson on finances. So the basic outline for our project today, we're going to introduce you our design, go through the fabrication and testing, and go through the final programmatics of our project. So an introduction to hydraulic trainers. They're used in commercial use as well as educational purposes to introduce users how and why hydraulics work and to show the differences between theoretical and actual performances. So our purpose is to design and test an electro-hydraulic control system for MELAB 4733 to introduce students into an integration of control systems and hydraulic systems. So this is the basic final product that we designed with all the major components labeled. Starting from the left side, we have our data acquisition, power supply, and circuit board. Following that, we have our actual hydraulic cylinder, load apparatus with the different weight plates on top of it, and string potentiometer for our feedback sensor. And we also have underneath the workbench the hydraulic power unit and spill containment, and as well as our proportional control valve, pressure gauges, and manual power switch. And so the basic idea of our project is to use LabVIEW in order to control the displacement of the hydraulic cylinder. So our primary objectives is to design our feedback control system, our data acquisition, and create a lab manual experiment for MELAB 4733, all of which have been met.
So while operating the hydraulic cylinder, will have a maximum displacement of 8 inches for average cylinder speed of 3 inches per second, and we'll carry a load of 25 to 100 pounds. The LabVIEW control system, we use an NIC DAC 9172 with various inputs such as the set point, the PID parameter, and the load. The instrumentation requirements for the system are a spring pot and manual pressure gauges. The control system will use a relay-based auto-tuning method. The closed control system will run in parallel with the safety system, and the control system will have plots of the hydraulic cylinder, the valve output, as well as a set point on the left and front panel. The safety system will have the pressure relief valve set to 350 psi. Also, the valve voltage input will have a fault monitoring system. The maximum displacement of the cylinder will be limited to 9.3 inches. And the set points allowed by the user will be constrained to a 0 to 8 inch set point range. Here are also the specs for the hydraulic system, the main components being the hydraulic cylinder with a 10-inch stroke, also the fixed displacement pump, which has a 0.5 horsepower pump and a 2.85 gallons per minute flow rate. Also, we have the proportional directional control valve for ratio metric coil.
So how we're actually controlling our experiment is with a proportional control valve. Inside the valve, there's a spool that moves left to right by an input of current. So as it moves left to right, it goes across the port openings, allowing fluid to flow in and out of the valve to the hydraulic cylinder. So this is a basic graphic of our experiment with the hydraulic cylinder and proportional control valve. So as there's an input current, the fluid will flow to the cylinder, and the cylinder rod will extend until it reaches its final setting.
For our main fabrications, we have to worry about the weights being held up by the rod. So we designed a load apparatus, which is threaded directly into the cylinder rod itself, and our string potentiometer is connected to the load apparatus to measure the voltage difference. That will give you a linear displacement, and the spring hot eyelet holder is fixed to the load apparatus itself. This is our main fabrication layout. As you can see, our adapters for the fittings are labeled and will be provided to the TA for any troubleshooting. The main adapter we are using is 3/8 NPT fittings and 90-degree NT fittings to measure the pressure. As I told you previously, these are our 90-degree fittings attached to the valve on both ports, and our T fittings are wet to wet to measure the pressure drop across the valve and make sure our system functions safely. And on the bottom of the bottom of the cylinder, you have a 180-degree fitting, and on the top of the rod, on the cylinder, you have a 90-degree fitting, and both the fittings on the pump are 180 degrees. So for our theoretical calculations, we use a program called electro-hydraulics. So it's basically a mathematical program. Like if you used Singular before, this is what it does for hydraulics. So it allows you to input certain amount of PI values that you calculated from experiment, and it allows you to put it into that PID bar. What it does is, once you put it in, it will give you a simulation to experimental versus what you should have gotten theoretical. So here's our wiring layout. It consists of basic power supply, breadboard, and proportional valve, and the NI DAC system. For our wiring system, we put a plastic around the wire because once you tap it or student taps it, it introduces noise into the system itself. So we wrap it around plastic, which limited the noise. Also, they are neatly labeled and they are provided to the TA for any other further troubleshooting. So here's our basic test procedures that we did before we did anything. Was our safety checks. Since we are messing with high power hydraulics, we have to make certain that hydraulics safety works as intended, and we did a couple of tuning methods and the analysis comparison of hydraulic experiment versus the simulation.
So here's a video of the relay-based auto-tuning method that we use in the lab manual. You see how the system is the cycle and sensor oscillations in process variable. This is used to capture the PID parameters, which will later be used to have a fully tuned system. Now we'll see the students actually using these PID parameters that were calculated. And we say response is fully tuned, and this will be done for all the set points and loads. So here we see the test result for all the set points and loads. These results will be used for the TA so that they can compare these results to the students' results. Here we see the associated numbers for each of the tabs that we just saw, along with the PI gains for each of those tests. Here are the various other tests we did, which include the pressure relief valve functionality test, the safety test, as well as the duration test. Here's an overview of the safety front panel. We can see how the TA has ability to change who is texted and who is emailed in case of a failure. We can also see how the states of wiring are shown, when there's a function with that, as well as the failures if there is any. Now we'll see on this test, we force the step up to 10 inches. And doing that, you see that the displacement of the cylinder stopped at 9.3 inches, so that it didn't go to the maximum displacement and injure the cylinder. We can also see how the student has ability. You can see how it showed what was the failure, and it shows that the safe state is on. So after that, we'll see how after the failure, it sent a text along with an email to the TA. Here are the risks for conducting the lab, which include faulty wiring, noise and calibration issues, software and computer malfunctions, as well as valve malfunctions. These will be alleviated with troubleshooting procedures included in the lab manual.
A portion of the final product will be a lab manual provided to the TAs of ME 4733, the Mechanical Engineering Lab, so that they can provide it to the students in order to operate the system independently. The focus of the lab manual will be an understanding of the hydraulic system that is under ongoing operation, and the simulation and the system identification techniques using both manual and auto-tuning methods. The lab will include a pre-lab, which has conceptual questions on the hydraulic systems under use, and it will provide step-responsive hydraulic system calculations to provide a basic idea of what sort of signal will be under operation. The procedure of the actual lab manual will include an introduction exercise, then move into the manual and auto-tuning methods for efficiency for a PID controller. It will then go into the system identification methods, which allow us to see the function of the system based on measurements, and a theoretical sim hydraulics comparison as a result of the previous procedures. The analysis will bring us to a data collection and system response plotting, which allows them to see the data graphed in the exercise in an Excel document, and the step response characteristics of each type of measure, each type of control. Percent difference between the natural frequency and the damping ratios for each procedure will also be able to be observed because of these for each type of tuning.
So this is an example of the kind of analysis that students will be doing for the experiment using the system identification techniques. In this case, this is a time domain method, and so this is able to characterize the response of the cylinder, giving the students the ability to calculate the damping ratio and natural frequency. And so this is an example of percent difference calculations that the students will do comparing the experimental results to sim hydraulics.
The whole schedule for this project was developed between the beginning of the semester in August and the completion of the project this week. And we have completed all of the available, all of the assigned tasks seen on our initial project Gantt chart. Our budget has equalized as of this week, and which leaves us with a cost performance index of 1.044 and the schedule performance index of 1.05, leaving us both on schedule and on budget. The bill of materials in total, including excluding labor done by HSNS, brings us to just over $3,000, most of which is provided by the University of Texas at China.
So in conclusion, we have reached and met all of our objectives, functional requirements, and as well as the time constraint. We ended up learning a lot through our experiment, and the project works as intended and can be used for ME Lab 4733 next semester in spring 2014. Are there any questions?
Good job.